understand now. So if you see this beam, clearly observe, is going up and down. Correct? This beam is going up and down. This is known as vertical bending of a beam. When beam is going up and down, it is known as vertical bending. If you see in next, this beam is bending in horizontal plane. All right. So this is left and right. And if you see the right hand side in which I have written torsion, right? If you see this beam is not bending up and down, there is a torsion of this beam. Now, torsion is altogether a separate unit for you people, where we need to study thin walled, open, closed, shear flow, shear center, all these things will come. As of now, we'll restrict ourselves to bending. Now, the next thing I want you people to understand is, if you people agree, if you want your beam to go up and down, which is vertical bending, you just imagine here, just see this movement X, which I have shown here in the image. Maybe I can show you the pointer. If you see this part, right? You see this MX will bend my beam up and down. All right. And up and down is known as what? Vertical bending. Up and down is known as vertical bending. And the movement which is responsible for vertical bending in terminologies in Megson or in any standard book, this movement is referred to as MX. Now, why MX? If you people see, this MX is rolling about x-axis. You can see like a snake rolling about a pole. And when this movement rolls about x-axis, right, this beam will go up and down. So this MX, if any load is applied, which is known as MX, that will bend my beam in vertical direction. That means it will go up and down. Now, next point, if you apply a movement like about y-axis, now you imagine this. Don't worry about the directions. We will see later. If you apply a movement like this, what you're trying to do is you're trying to bend your beam in horizontal direction, and hence this will give rise to horizontal bending. So horizontal bending is one in which your beam move left and right. The moment is applied about y-axis, and hence just for easy learning or just for easily remembering this, we name it as My. So My refers to horizontal bending, Mx refers to vertical bending, and why Mx? Because this movement Mx is rolling about x-axis, which will give us movement about x-axis means up and down. And if you see y, this will give us movement about y-axis, which will bend my beam in horizontal direction. So you have clear visibility of vertical and horizontal bending. Now, if you people observe this, I hope it will be clear. If you apply a movement about z-axis, you imagine something like this will happen. It will twist your system. So about z-axis, about this z-axis, you will be having torsion. So you will calculate all the properties with respect to z-axis later in torsion unit. As of now, we are in bending. All right. Now, another thing I want you people to understand is, if you see movements, because your cross section is in XY plane, I'll repeat this again, because my cross section is in XY plane, I have a movement which is rolling about x-axis, so Mx. I have a movement which is rolling about y-axis, which is My. So you will not see any Mz in bending. Mz, which is movement about z-axis, which will try to twist my system, will come in torsion. So as of now, we don't have any Mz. We will only focus on bending, which is Mx and My. So I just need a quick nod. And now why this thing is needed, let me just quickly show you. If you see this, right, this is the reason you are studying this in your aircraft syllabus. If you see your aircraft wing, you can clearly observe that wing is clearly prone, or it is very difficult to manage this, is subjected to vertical bending. This is the reason you have cantilever beams, deflection problems, stress calculations in your syllabus. So I hope this is very, very much clear to you people. What is bending? What is cross section? What is XYZ coordinate system? And if it all this is clear, then I'll go back to my presentation mode and I will start developing equations on this. Is this clear for everyone? Guys, okay? Okay. Now I'm back to my presentation so that I can develop equations. I have framed this lecture completely. Even if you don't know anything about bending, by the end of this, you should be in a position to solve any numerical or any difficult questions which comes for bending. All right, let's solve this now. Okay, perfect. So this is the slide which I have already shared. So there is no difficulty in this. This is the reason I was saying if you apply a moment about x-axis, so you are simply trying to make beam up and down, which is vertical bending. If you apply a moment about y-axis, that means you just try to make your beam go left and right. This is horizontal bending. And if you apply a moment about z-axis, in simple words, you are trying to apply a moment like this, which is about z-axis. This is your z-axis, right? So you will twist your beam, which is altogether a separate unit. Now let's go to an equation which is very, very difficult equation when we go to Megson. And this is your aircraft application. You have already seen this. This beam, this is the cantilever beam which is fixed here. And if you see, this beam is bending up. So this up and down is nothing but vertical bending. But we're not going to study only vertical. We will see both horizontal and vertical. Now, I'm coming to a very difficult equation, but believe me, I will try to make it simple for you so that we can solve any numerical. Gate numericals are very simple and straightforward ways. That is not my concern. The concern is sometimes they ask a difficult question combining bending, torsion, and all these questions. So let's go slow in this. So if you see, this is the length of the beam. Please focus very hard for next 10 minutes so that you can understand this equation. This is the length of the beam. It may be fixed somewhere. And if you see, this is my cross section. All right, this is the cross section of this beam. Here you have seen cross section as I. Here you have, I'm just giving you an example with circle, and then you can have rectangle, you can have C section, anything. Now you are clear what section means. Now in this cross section, if you people see, this is my x-axis. Guys, please listen to me very carefully. If you see, I have taken another example in which my cross section is rectangle. Here, my cross section is circular. Any shape, I don't bother. Then this is the x-axis. Now I want you people to be clear in this. When I say x-axis, at this point, we will see this is centroidal axis. X is 0 here. At this point, if let's say this dimension is 10, you will say x here is 5 and you will say x here is -5. I hope this is clear. Everyone understood what is -5, what is +5 because total length is 10. Similarly, if you go here, you will say this is -y, this is +y. And similarly, if you go to this point, you will say this is x5 and let's say y5. So this coordinate is 5, 5. So this is how cross section varies in xy plane. All right. First thing I want you people to be very much clear because they will say calculate the maximum stress, calculate the stress at this point, blah, blah, blah. Many numericals will come, right? Now, what next thing to understand here? If you have a moment about x-axis, which is mx, so you are rolling about x-axis. So the inertia about x-axis will be calculated. Now I will do all the calculations today for inertia, how to calculate for circle, rectangle, C, I, Z, any cross section. We will solve everything today. But what I'm saying is when you have x-axis, mx, and you know this is vertical bending, the inertia will be about x-axis, which we name it as ixx. I will give you the properties in some time. So if you see, I have written it here. If you're rolling anything about x-axis, the moment is mx and inertia is ixx. Then, if you roll anything about y-axis, your movement is my and inertia will be iyy. And if you rotate anything about z-axis, your movement will be mz, which typically we write it as torque T. Don't worry about it. And your inertia is z. So you have three inertias, ixx, iyy, izz, and you have three movements, mx, my, mz. But if you people see, bending will only happen because of two people, mx and because of my. Forget about mz for now. So we will not bother about this axis because I am not interested in twist of the section. I'm only interested in bending of the section. So if you clearly observe this bending equation, right? I'll explain you what is axisymmetric, what is symmetric in few minutes. No. Buckling is entirely different, Girish. Please don't get into it. I will come to that. So if you see a right-hand side equation, right? First thing you observe here is that you have two brackets. One is with y and the other one is x. Because your cross-section is in x and y plane, if you see, your cross-section is in xy plane. And the moment which you can apply are only mx and my. So what I want you people to see in this equation is, this is easy to learn now. Because your cross-section is in xy plane, you have two brackets here. One is y, this term, and another one is with x, this term. And if you see the loads in the sense moments, you see there is only mx and my. There is no concept of mz here. So you will not see mz throughout your bending. There is no mz concept. There is no z-axis we were worrying about. So if you see mx, my, mx, don't worry about why it is where. As of now, we just need to learn that there are movements present, which is mx and my. All right. Now, next. So this is somewhat clear. Now, when we have x-axis, when we have y-axis, when we have movement mx, when we have movement my, the inertias will be ixx, iyy, and we will learn slowly ixy. But if you see the entire equation on right-hand side, right, is only in terms of x and y, because your cross-section is in xy plane. This is one thing which should be crystal clear to everyone. What do you mean by this equation? I'll tell you what is sigma z later. But as of now, is this clear for everyone? Why this whole equation on right-hand side, if you observe, is completely in xy. You see, it has xy terms, it has mx, my, and it has all the inertias about xy plane. Don't worry, what do you mean by these quantities? I don't expect you to know this. But at least you should know in this bad equation, everything on the right-hand side is in xy because your cross-section is in xy plane. Give me a quick nod if this is clear for everyone. Then I'll go ahead. Is this okay? Clear for everyone? Anything, any doubt, any misconception you want me to repeat? Just let me know. I can give it detail. All right. Now, let's see what this sigma z tells. I don't know whether I have kept an image. No. Okay. Still, I can explain you that. All right. Now, see what happens. When you have a beam, right? I think I've kept some image. I think, yeah, I can show it from here. Please listen to this carefully, what I'm trying to explain here. Any cross-section, Akash, your cross-section is in x and y plane. The bending is not occurring in xy plane. I told you, right? You have assumed your cross-section is in xy plane. See, this is x and this is y. This is x and this is y. This is your cross section, right? This is x, this is x, and this is y. So your cross section is in xy plane. Plane is 2D, right? Clear, Akash? Yeah, yeah. Now, guys, I want you to understand one thing before going into that equation and start solving some numericals. When you bend a beam, right, you can see this is vertical bending, right? This beam is going up and down. So if you see it from this end, if you see it from this end, you will see something like this, which I have drawn this diagram. If you see what happens here on the upper section, this section, you are compressing it. You can imagine this in your mind. And if you see this below section, right, this section, this is in tension. You can see what will happen. And if you keep on bending this, right, what happens? This system will break from center. It will be divided into two sticks, two pieces. Now with this, what I'm trying to explain you here is when you bend a beam, right? When you bend a beam, the stresses which are known as bending stresses are generated. And these bending stresses are nothing but normal stresses which acts perpendicular to cross section. Now, imagine or visualize this in layman terms. When you bend any system, right, what ideally beam experiences as if someone is pulling me in this direction and this direction, as if someone is pulling me. Although you're not pulling this, you are bending the beam, but structural experience is as if someone is pulling me in this direction. Now, what do you mean by this? Let me make it more clear. When you have any beam like this, and you bend it by any amount, I'm not interested in which direction you're bending it. So what happens is, guys, please listen to me carefully. Its cross section experiences normal stresses, which is represented as sigma z, and similarly there will be stresses here. Now, what is a normal stress? A normal stress is one which is perpendicular to cross section. Correct? What is the cross section variables? If you people agree, your cross section is in x, y plane. So anything which is perpendicular to it will be z. Correct? And this is the reason you find sigma. Sigma here represents normal stresses going in z direction. So guys, what I'm simply explaining you is, if you have your cross section in xy plane, if this is x and this is y, that means you have moments mx and my. And if you apply these moments, you will get stresses which are perpendicular to it going in z direction, and hence you have sigma z. This is the most beautiful equation which is present in Megson. You must have seen this in your academics. If not, perfectly fine. You will be doing this in your maybe third year or something. But I hope everything, at least learning formula is different, but at least you people understood that what do you mean by this sigma z? This sigma z are nothing but your bending stresses. Bending stresses means the stresses which is coming because of bending. What are these stresses? These stresses are nothing but stresses which are perpendicular to cross section. Now, question in your GATE exam, they will ask is, what is the maximum bending stress and where it occurs? So stresses acts on complete cross section. Your stresses act here, 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 here. Everywhere in cross section, stresses are acting. All these stresses are perpendicular to cross section, as if you're trying to pull this beam. out of all this, in your cross section, where is the maximum bending stress is what your gate numericals are. And your complete Megson also saw on this. Any exercise or solved examples, if you see, right, you will be talking about this maximum bending stress, which will be calculated using this formula. Now, I want to go one step further. The next thing we need to understand is, first of all, how we learn this formula. All right, let me give you a hint. So what I do is, or you typically try to follow this, you write two terms as this, y and x. Because your cross section is an xy, you write in this way. Then you, in both the terms, you write your denominator like this, ixx, iyy minus I square xy. I'm telling you how you should remember this because this is asked completely in your GATE exam. So you calculate, you just write these terms. Then once you see y here, you first write your iyy. You see x here, you write ixx. All right. Then once you have written iyy, then you write opposite moment mx. Here you have written ixx, so you have written my. Minus in both. If mx is covered, my will come here, my is present, mx is come here, and then you have ixy. Anyhow, we will learn this formula when we start solving numericals. But you will see why this formula is in this form in just maybe next 2-3 minutes. Now, what this equation explains you, and second, what is the meaning of this axisymmetric section? All right, now please listen to me very carefully. If, and I want you people to answer this, I want you people to give it a try, answer my question. If you want your beam to bend in vertical plane, although I have written it here, the moment we want is mx. If you want your beam to go up and down. If you want your beam to go in horizontal plane, the moment you apply is my. My question is, if I apply both moments together. So guys, this is only mx. If it is only mx, your beam will go up and down. Only mx. Yeah, that means my is 0. No one is forcing it to go left and right. When you see this, this is my only, and mx is 0. Means it will go left and right. No one is telling it to go up and down. But if you do both these things together, that means you apply horizontal bending also and you apply vertical bending also together in one shot. Now my question to you people is, you have applied both mx and my. What do you expect? Your beam will go up and down, guys, or your beam will go left and right, or something else? What do you people expect? Okay, good, 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 Archishman. Archishman told me that it will be inclined. That's perfect. Now, what do you mean by this? The meaning of this is in diagonal XY plane, perfect, Sridevi. So meaning your beam will try to go up and down, but it will also try to go left and right, meaning maybe it will bend something like this. I hope you, I'm just giving you an example. So it will not bend only up down. It will not bend only horizontal. But because you have both the people pushing sidewards and upward downwards, you have bending maybe at some plane. This bending, which is not only in vertical and not only in horizontal, but in some other plane means some inclined plane, is known as unsymmetrical bending. Sometimes people also say this as asymmetric bending. So what is unsymmetrical bending, guys? A bending which happens in a combination of two planes or in an inclined plane. So the best example of symmetrical bending is this. This is symmetrical in vertical plane. This is symmetrical in horizontal plane. And if you go in some other plane, it is known as unsymmetrical bending. So from now on, if anyone, guys, this is one very common question asked in interviews. So if anyone asks you what is the difference between symmetrical and unsymmetrical bending, you directly say unsymmetrical bending means unsymmetrical bending occurs in some inclined plane. And what is symmetrical bending? If you have pure vertical or you have pure horizontal, either one of them, both are known as symmetrical bending. Give me a quick nod if this is clear to all of you. Then I will go further into equations. Is this part clear to all of you? Perfect. Good, good, good. Now, the next thing I want you people to understand is, although I will calculate for all cross sections, but please take this as a note for time being. If you have any cross section which is symmetric, all right, now please listen to me very carefully. Any cross section which is symmetric. Now, what is symmetric cross section? A rectangle is symmetric about this axis, right? Symmetric means left and right is same. And rectangle is also symmetric about this axis, means up and down is same. You can easily imagine the word symmetric, right? So this is a double symmetric cross section. Rectangle is a double symmetric. X-axis also symmetric, Y-axis also symmetric. Similarly, if you see circle, if you cut, you have two similar, this is symmetric. And if you cut it vertically, it is also symmetric. So this is also symmetric cross section. If you see I section, this I section is symmetric about Y-axis, left and right are mirror image. And this I section is also symmetric about X-axis. That means top and bottom are also same. Now what I'm trying to portray here, I will show you this slowly because I have all the slides for calculating inertias. But what, just as of now, please remember this. When your cross section is symmetric, all right, whether it is single symmetric or doubly symmetric. Now I'll give you an example. If you see C section, this C section is symmetric about only X-axis. You see, top surface and bottom surface are exactly same. So it is symmetric about X-axis, but it is not symmetric about vertical axis. So if you see, it is not mirror image about any vertical axis. So this is known as single symmetric cross sections. All right. And if you draw any cross section like this, you see, it is neither symmetric about X-axis. It is neither symmetric about Y-axis. So don't worry, I have all the numericals for all these cross sections. As of now, what I want you people to remember is whether the cross section is single or doubly symmetric, IXY will be 0. And I will name this, I will write properties. I have all the slides for calculating inertias for different cross sections. So please don't bother about, I have taken everything in this slide to make you about the properties and about C sections. We will do that all slowly. As of now, just take this note so that you know this equation properly. So just keep one thing in mind. If IXY is symmetric, if your cross section is symmetric, single or doubly anything, IXY is 0. Keeping this in mind, I want you people to understand one thing.